We're going to use our tools of torque and force now to consider what we call equilibrium problems. Equilibrium is a situation where the sum of the forces acting on a system is zero and the sum of the torques acting on a system is zero. By Newton's laws, that means that the linear velocity and the angular velocity of this system will be constant. The condition of static equilibrium is when those quantities, velocity and angular velocity, are not only constant, but they are also zero. In other words, the object is completely at rest, or the system of objects is completely at rest. Until recently, the free body diagrams we've drawn were simple prior to considering torques because all the forces on an object acted through its center of mass. So we might have some object, and there would be several forces, but they all really kind of ignored the shape of how the object itself. So we said, well, acceleration is zero whenever the sum of the forces is zero. Now we're going to treat the objects as extended and having some shape, and not all the forces exactly act at the center of mass. Some might be out at the perimeter, some act through the center of mass, some act out the corner, what have you. That means that we're going to have to consider two separate conditions. One is when the sum of the forces is zero, and the other is when the sum of the torques is zero. Because remember, a torque is a force acting at some radius away from a pivot point. Where do forces act? Well, it's important to kind of recognize that. In some cases, it goes right through the center of a block. For example, when we think about why some blocks tip over, it's because some forces act through the center of mass and some forces don't. Gravity always acts through the center of mass of an object. So the block that's resting firmly on the table, well, it sort of stays that way because its gravitational force pulling downward pulls right across, from the center of mass right across its base. Even if the block is tipped a little bit, the gravity points across from the center mass straight down, and that's still to the left of that pivot point right there. And when we can tip the block a little bit further, now it's going to fall, because in this case, gravity acting through the center mass is on the right-hand side of that pivot point, and it starts to rotate. So tipping in this case results from a net torque, which comes from a force that came from the center of mass. Only gravity exerts a torque here. There's another force that's acting, which is the normal force from the table, and that's always pushing straight up from the point of contact with the table. In the case where the block is firmly on the table, then in this case the normal force points up from the center of the table on the block. In the case where only the pivot point is in contact with the block, well, then that's where the normal force is going to be exerting. If we consider that the pivot point, then it doesn't exert a torque, because a torque is an R cross F, and R is zero in this case. So it's only the gravitational force that exerts a torque. And in this case, the case where the block is tipped over far enough, the torque is such that the block starts to tip over. Think about a book falling off of a table. Gravity, again, always acts through the center of mass of an object, and the normal force acts up either through the point of contact or the last point of contact with the book on the table. So in the case where the book has got its center mass out over the edge of the table, now it's going to start to fall because gravity starts to exert a torque. So these are the kinds of problems we're going to be doing, and we're going to ask, when does the object stay still and when does it start moving?